Second paper in the running section of class here is this one here, Joyner, 1991, called The Optimal Marathon Performance on the Basis of Physiological Factors. This is a paper actually from the exercise physiology literature, not from the biomechanics literature. So those of you who have taken Kines 360, which for the non-Kines majors in the class is the kinesiology undergrad core exercise physiology class, you should see some terms here that are familiar to you if you've taken that class. This is of relevance to us in a biomechanics class because while it's not a paper in the biomechanics literature, it involves some mathematical modeling and it involves an element of mechanics in especially in one of the key terms in the key model or key equation in this paper here. The author of this paper, Mike Joyner, is a well-known exercise physiologist at the Mayo Clinic in Minnesota. And he got a lot of attention recently for this paper, which is now, let's see, how long ago was 1991? That was 2001, 2011. This was coming up on 30 years ago. So this was quite a while ago that he published this paper. Notice here, if you look down about 3/4 of the way through the abstract here, he predicts, and remember this was 1991, that the fastest time for a marathon that can be predicted by his model here is a little bit under 2 hours, 1 minute and 57, 1 hour, 57 minutes and 58 seconds. And if you pay any attention to the marathon running world, you will see that somebody recently ran a marathon pretty close to this speed, dipping just a little bit under 2 hours. There were some special circumstances involved, and it's not actually the official, formal, recognized, ratified world record. There's another time that was run in an actual race is the world record, but it did indeed line up here with what Joyner's prediction nearly 30 years ago was for what kind of the maximum human potential for running a race like the marathon is in terms of the fastest time that somebody could run the marathon in. So this paper is kind of our first dip into the sport performance side of running. The previous paper from the first lecture there, the Novacek review, was just kind of a general review of the mechanics of endurance type running and some descriptive issues for kinetics and kinematics and electromyography and muscle mechanics and energy expenditure and things of that nature. A lot of that is true of running at all levels. So a lot of the things that you read in that paper apply to running at all levels of skill, all level of ability, all forms of running, recreation and competition and sports and all forms of running. This one here is specifically about running as a sport and running at the elite level for sport and for competition. So athletes who train to run for a living for their profession, training to run a marathon as fast as possible. This is a fairly short paper. The key bit of it here is early on and is this equation right here. This equation right here that I'm trying to highlight but not having any success in. But the equation here on the second column of the first page, a little way down where it says marathon running speed equals some things here. And let me write that equation out for you if you're not real sure what those terms are there. What Joyner is proposing there is that the maximum speed that somebody can sustain over a marathon, and if you're not in the running world here, a marathon is 26.2 miles, or about 42 kilometers of running. Okay? The current world record for the marathon is 2 hours, 1 minute, and 39 seconds, I believe. It was run by a year or two ago by a Kenyan athlete named Eliud Kipchoge. And if you work that out to the pace per mile, this works out to below a 5-minute per mile pace for running 26.2 miles. So if you want to humble yourself a little bit, and don't do this unless you are a pretty experienced and fit individual with running on treadmills. This could be dangerous. But if you're confident in your treadmill running ability, next time you're on a treadmill, hop on it and set it to set it to a speed of like 6. That would be about a 10-minute mile. And then slowly inch it up to 12, which would be a 5-minute mile. And just feel what that effort is like. Or maybe inch it up a little bit above 12 and feel what the effort of a sub 5-minute mile is like. And then imagine doing that for 26 miles or for a little bit over 2 hours. It's pretty impressive and pretty humbling to recognize the type of running that these elite folks that run the marathon for a living and for a profession are doing in their efforts in that race. So his equation here that Joyner proposes for figuring out what's somebody's marathon running speed is it's a combination of three variables multiplied together. It's your VO2 max times your fraction of VO2 max at LT, which I'll explain in a little bit here. And let's separate these off a little bit just to make it clear. And then we divide that by RE, which is your running economy. Oh, sorry, we multiply that by RE, which is your running economy. Okay. So these three terms in here, VO2 max, this is your maximum rate of oxygen consumption. Races like the marathon, where you're going to be sustaining your effort for at least 2 hours. I guess most of you are probably going to be running, if the students in the class or somebody like me were running a marathon, it'd be more in the 3, 4, 5 hour range, depending on how fit you are. That's what's called an aerobic effort or aerobic exercise. Aerobic here is a fancy word for oxygen, and it's aerobic exercise because when you're exercising at those intensity levels where you're going to be sustaining the effort for several hours at a time, you're utilizing primarily what's known as aerobic metabolism inside the body. These are chemical reactions inside the body that use primarily oxygen molecules combined with some other molecules to produce ATP molecules. ATP is adenosine, I can spell this right, triphosphate, which is the molecule that our muscles use for fuel, for the muscles to produce force and perform work on the skeleton and move the body around in movements like marathons or in movements in general. The other end of the coin here would be anaerobic exercise, which is exercise at a higher intensity level where you're exercising for, say, minutes at a time or seconds at a time rather than hours at a time. And the anaerobic here is kind of the opposite of aerobic. You'd be converting glucose in the absence of oxygen directly to ATP and powering the muscles that way. But for an effort like the marathon, we're not using a whole lot of anaerobic metabolism. We are producing most of our ATP to power our muscles for an effort like that through aerobic metabolism or through using oxygen primarily as our fuel. So when you're doing an effort like the marathon, since oxygen is all around us in the air that we breathe, you're not limited by the availability of the fuel. You're limited primarily by the ability of your body to supply that fuel to your muscles. And that's what the VO2 max is. It's the maximum rate at which you can consume and supply oxygen to your body and to your muscles to power the pathways of aerobic metabolism and produce ATP and use your muscles for an effort like a marathon. Some of you may have done a VO2 max test. This is typically a graded test on a treadmill, and you'll start at, say, a certain speed, and then every couple of minutes you'll increase the speed or increase the incline, and you'll be attached to a machine that's hooked up to a computer while you're doing this, that's measuring your rate of oxygen consumption. And you'll keep every few minutes either increasing the slope of the treadmill or increasing the speed of the treadmill, and basically keep doing that until exhaustion. And the maximum rate of oxygen consumption measured before you're exhausted is your VO2 max. Okay? Now, you obviously can't sustain that rate of effort for 2 hours or 3 hours or for a marathon type distance and duration. And so the second factor in here in the Joyner equation for marathon running speed is the fraction of VO2 max at LT. LT here is lactate threshold, and that is the intensity of exercise as a percentage of VO2 max that you can operate at before your muscles start accumulating lactic acid. Okay, that's your lactate threshold. It's actually a little bit more complicated at that. It's when the rate of lactate production in the muscles exceeds the rate at which your body is able to remove the lactate from the muscles. Okay? And then you start accumulating it in the muscles, and eventually your ability to hold that intensity of exercise when you're above your lactate threshold will decline, and you'll have to slow down or stop. For a marathon or something like the marathon, unless it's a special circumstance where you're like going uphill or downhill or something like that, typically you want to sustain a constant effort throughout the entire race. You want to keep your pace pretty steady. So that's why the second term in the equation here is this fraction of VO2 max that you can sustain before you're at your lactate threshold, or when you're right on that red line between accumulating lactate faster than you can shuttle the lactate out of the muscles. Okay, neither one of those two factors here, the VO2 max or the lactate threshold, have a whole lot to do directly with biomechanics. This third term here has a lot to do with biomechanics, and this is running economy. Okay? This is typically defined as the speed that you can run at divided by your VO2, or the rate of oxygen consumption. Okay? This will typically, so notice that this isn't VO2 max, this is VO2, just the rate at which you're consuming oxygen to run at a certain speed. It may or may not be your VO2 max depending on what speed you're actually going at there. Okay? So this would be measured typically similar to the VO2 max, where you would have somebody running on a treadmill and you would put them at a certain speed, and then you would measure the rate of oxygen consumption, or the VO2, while they're running at that speed. So if we wanted to see like who in the class is the most economical runner, we might put all of us on a treadmill and have us all run at some common speed and then measure the rate of oxygen consumption. And whichever one of us had the lowest rate of oxygen consumption to run at that fixed speed would have the highest running economy, would be the most economical runner, and would have the highest or the fastest predicted marathon running speed. Okay. Now, this third factor here has quite a bit to do with biomechanics, because the mechanics that you use to run, the specific form that you use to run, or your style of running, can have, in some cases, a very large effect on your running economy, on the rate of oxygen consumption that you need to run at a certain speed. So just a short list here of some of the many factors that can affect an individual's running economy when they're trying to run at a certain speed. Your foot strike pattern can have an effect, right? The posture of the foot when you strike the ground, whether it's a heel strike or a rear foot or a toe strike or something in between, can have an effect sometimes on running economy. The shoes that you wear can have an effect on your running economy. Kipchoge, when he broke the 2-hour marathon barrier here, was wearing a special pair of prototype Nike shoes that you can see down here. I can't remember if they had a name at the time, but since they've been released to the public, or at least a version of them has been released to the public, they've been named the Alpha Fly, and it is this shoe here. There's a number of features of this shoe, of design features of this shoe, that differ quite a bit from a typical running shoe or even a typical expensive marathon shoe, and we'll talk about some of those features in some studies on those shoes a little bit later in class. But the style of the shoe, or the type of shoe, the features of the shoe can indeed have a big effect on your running economy. Stride length, and related to that, stride frequency, or something you typically see this called step frequency, can also have a big effect on running economy, or just more general mechanics, things like the pattern of your knee motion, the pattern of your hip motion, your arm swing, just the general features of your mechanics that you use to run can all have ranging from tiny to large effects on the oxygen cost of running at a certain speed, and thus affecting your running economy. Okay? So take all three of these things, the VO2 max, the fraction of VO2 at your lactate threshold, and your running economy, multiply all those things together, and if you do that, you'll find the units work out to being meters per second, and that meters per second is not coincidence that it has speed units there. That is your maximum predicted marathon speed here, according to the Joyner equation here. And is this an accurate prediction? Is it an inaccurate prediction? Turns out that it works pretty well, at least a lot of the time. And his prediction that he made for the maximum possible human marathon speed, at least at the moment, seems like it's pretty accurate. We're still a couple minutes away from what he predicted there in terms of the fastest possible marathon speed, and maybe we'll start approaching that over the next few years or next few decades or next few centuries. Okay, that is all for now for this lecture. Like I said, this is a short paper, so we'll have a pretty short lecture. Again, these are three factors here that can affect or that at least we suspect affect the maximum sustainable marathon running speed. And I should emphasize in terms of the broader picture in sports that this relationship here isn't unique to marathons. You could also develop a similar relationship using these same three terms for pretty much any intense long-term aerobic effort. So like bicycle racing or endurance swimming or rowing, other aerobic efforts that are predicated primarily on aerobic metabolism and oxygen as fuel. This equation would also apply with relevance to those sports as well. You can also use these to reason out which athletes might be really, really good at sports like marathon running. For example, if somebody has a really high VO2 max, they might then possibly be a pretty good marathon runner if they can sustain a high fraction of that max and are also an economical runner. I am not a great marathon runner. I had actually a very high VO2 max. I don't think I could do it now, but when I was younger, I had a VO2 max of close to 70, which is pretty high. But I'm really, really bad here. I can't sustain a very high fraction of that VO2 max at my lactate threshold. So at least that's one of my many excuses for why I'm not a great marathon runner, despite having a pretty high VO2 max here. Lance Armstrong, the disgraced bicycle racer, who I guess technically has never won the Tour de France, but let's be honest, he won the Tour de France 7 times, actually had a pretty pedestrian VO2 max for a world-class cyclist. I think it was in the low 80s or so, which is, of course, incredible for the general population, but is not terribly impressive for a world-class cyclist. But he had an absolutely incredible lactate threshold. He could sustain like 90% of his VO2 max indefinitely for hours and hours and hours at a time. Or maybe somebody just has really good form or really good shoes or some combination of really good form or really good shoes, then they could get away with having maybe not such a great VO2 max or not such a great lactate threshold and then still be a strong marathon runner. But if you want to be world class, if you want to be best of the best, world record setter and compete at that level, you need all three of these things: a high VO2 max, high lactate threshold, and really, really good running economy. Okay, we will see you next time.